Now we're going to look at Descartes' rules of signs, and this is basically going to help us kind of eliminate some of our possible outcomes that we produce with the rational zero theorem. And that will make our synthetic division testing a little bit easier. So the rule of signs here basically has two parts. One, you're going to check how many positive real zeros there may be. And then the other one is we're going to check negative real zeros and how many there could be of those. Now, in checking that, we're looking at taking f of negative x and substituting that in and looking at the sign changes. But we're just looking at the sign changes. So, for example, when we take a look at this function here, we're going to just count the number of sign changes. So positive 3x to the seventh, and then minus 2x. So we've got one sign change there. From negative 2x to the fifth to minus x to the fourth, there's no sign change. But in the next one, there's another sign change, so that's 2. And then we can also see there's 3. So right now, according to the number of positive real zeros, it's either the same number of sign changes, so there's either 3, and then or we take a look at this, less than the number of sign changes of f of x by a positive even integer. So basically we're saying 3 minus, well, positive even integer that we could subtract from 3 would be 2. So what we're really saying is there's either 3 or 1 positive real zero. And when we look at the negatives, we have to take a look at substituting in negative x into the polynomial. So this will be negative 3x to the seventh when we plug that in. Remember, if we're going to substitute negative x into an odd power, the sign will change. And this was also how we looked at checking even and odd functions. That sign will change. X to the fourth will still be minus x to the fourth. Plus 7x squared will stay the same. Minus x, because that's the power of 1, so we got an odd power. And then just minus 3 stays the same. So when we take a look at sign changes here, we have 1, we have 2, 3, and 4. So this basically says there's either 4 or 2 or 0. And the 2 comes from just saying 4 minus 2. And the 0 possibilities comes from this less than the number of sign changes by a positive even integer. All of this statement here is us performing this 4 minus positive real. Positive even integer would be 4 minus 4. That would be the 0. So negative real roots in this one, we could have 4 or 2 or none. And we'll look at an example and see how this Descartes' rule of signs can help us eliminate some of the possibles that were determined by rational zero theorem. We're going to go through this process of, first, we're going to check the rational zero theorem. So remember, to figure out the possible roots, we're saying the factors of the constant over the factors of the leading coefficient. So I'll just say factors lead. And when we do that, we're going to see that we have plus or minus 1, positive or negative 2, positive or negative 4. Because 4 was our constant. In this case, our leading coefficient is just 1. So right now we have 6 possibles, and I'll list them: negative 1, positive 1, negative 2, positive 2, negative 4, and positive 4. So now let's employ Descartes. So Descartes' rule of signs is going to produce for us, well, if we take a look at the positive real zeros, it's going to tell us, we could be able to see if we take a look at all the sign changes, well, there are none. So there are none. There are no positive reals. Real zero. So that tells us something about this list. It there are no positive reals, we can eliminate positive 1, positive 2, positive 4. Now the only ones that are possible are negative 1, negative 2, negative 4. And just to check the rest, let's see how many negative reals it tells us there may be. So negative real zeros, we have to perform this step of inserting negative x. And when we do that, we'll see that we get negative x to the third. The next sign will not change because it's x squared minus 5x and then plus 4. So we look at all the sign changes. There's 1, there's 2, there's 3. So this agrees with our idea of possible outcomes from the rational zero theorem, which means there are 3 negative real zeros, or there might only be 1. If there's only 1, that means 2 of them would be complex. So right now we have a possibility of all 3 of them being the 3 we see here, or one of these 3 plus 2 complex. So how do we do that? Well, we pair that up again with synthetic division. But we know now we're going to test these 3. So let's test with synthetic division. Let's test the first one. Let's test negative 1. So we've gone ahead and done the synthetic division, and we can see that this one is actually one of our roots. So x plus 1, since it's a negative 1, is our actual root, and then multiplied by x squared plus x plus 4. And that equals 0 because we're solving for the roots. So now we have to determine, is negative 1 going to be the only one, like we said here, and then there's 2 complex, or are all 3 of them going to work? So inspecting this quadratic will tell us there are not going to be any other real roots here. Look at the discriminant, and it'll tell us if there are any more real roots or the real roots don't exist. So 1 minus 4 times a times c, 1 minus 16 gives us negative 15. The discriminant tells us that the other 2 are complex. So there's only 1 real negative root, and the other 2 are complex roots. And this also agrees with our fundamental theorem of algebra. So what we've done here with Descartes' rule of signs is we've taken everything that we've been using, synthetic division, rational zero theorem, linear factorization theorem, and we're putting those all together. But we're helping to kind of eliminate some of the possible outcomes from the rational zeros theorem. And you can also do this on the graphing calculator by checking to see where this actual function crosses the x-axis.